Let's talk about a force that's all around us, every single second. It's completely invisible, but it's powerful enough to shape our entire world, from the weather outside to, well, this.
So you're looking at a totally normal empty soda can. And in just a moment, it crumples in on itself with incredible force, almost like it's been squashed by some invisible giant. So what on earth is powerful enough to do that?
You know, the setup for this is actually super simple. You just boil a little bit of water inside an open can, which fills it with steam and pushes most of the air out. Then you seal it up tight and give it a quick bath in some cold water. The result? Bam! Instant dramatic crush. So let's figure out what's really going on here.
Okay, so the culprit behind our crushed can, it's something we are all experiencing right now, this very second. It's this unseen, powerful, and yes, crushing force that's literally everywhere.
And that force has a name: atmospheric pressure. Now the key phrase here is weight of the air. That's right, the air all around you, the stuff you're breathing, it actually has weight, a lot of it.
The easiest way to think about it is to just imagine a giant column of air that starts at the top of your head and stretches all the way to the very edge of space. All the air in that huge column has mass, and it's constantly pushing down on you. That's atmospheric pressure in a nutshell.
And why does the air have weight in the first place? Well, for the exact same reason you do: gravity. The Earth is constantly pulling down on every single molecule of air, and all those little tugs add up to create the pressure we feel. But here's the thing, this pressure isn't the same everywhere. If you're standing at sea level, you've got that entire column of air pushing down on you, so the pressure is high. But if you climb a tall mountain, well, there's a lot less air above you, which means the pressure is way lower.
Okay, so now that we've got the basic idea down, let's put it to work. It's time to finally solve the mystery of that crushed can, and maybe even look at another everyday object in a whole new way.
So, back to the can. Here's the secret. When we boiled the water, the steam pushed almost all the air out. Then we sealed it. When we cooled it down, all that steam suddenly condensed back into just a few drops of liquid water. That created a massive pressure drop inside, basically a vacuum. With almost nothing pushing out from the inside, the huge atmospheric pressure on the outside had no problem crushing that can flat.
This brings me to another question, something you've probably done thousands of times. When you use a straw, it really feels like you're pulling the liquid up into your mouth, right? You're sucking it up. But is that actually what's happening?
Well, not quite. When you sip from a straw, what you're really doing is removing the air from inside it, creating a little zone of low pressure. And guess what does all the work? The higher atmospheric pressure that's always pushing down on the surface of your drink. It shoves the liquid up into the straw to fill that low pressure space. So you're not pulling the drink up, the atmosphere is pushing it.
So we've covered the pressure from a gas, our atmosphere. But what happens when we switch from air to water? What happens when we dive in? The same basic idea is at play, but a couple of new things become really important. In any liquid, the pressure you feel really comes down to three main things: how deep you are, how dense that liquid is, and of course, good old gravity, which is always pulling everything down.
Now, depth is the most intuitive one. It's just like the air. The deeper you go, the more stuff is on top of you. More water means more weight, which means a lot more pressure. If you've ever dived to the bottom of a deep swimming pool, you've definitely felt this in your ears.
And here's the perfect way to see it for yourself. If you take a container of water and poke some holes at different heights, you can literally watch the pressure difference. The water from the very bottom hole is going to shoot out the farthest because it's under the most pressure from all the water stacked above it.
So far, we've been talking about these ideas and concepts, which is great, but this is physics, and that means we also have a tool to be super precise, a formula that lets us calculate this force exactly.
And the formula itself is actually pretty beautiful and simple. P equals rho GH. That's it. It's the mathematical version of those three factors we just talked about: the density of the fluid, gravity, and the depth. Let's just break that down really fast. P is for pressure, and we measure that in pascals. That funky-looking P is the Greek letter rho, and it stands for density. G is the acceleration due to gravity, which is pretty much constant on Earth, and H is for the depth, or height, of the liquid above you. Okay, let's put it to the test. Let's say you're a diver, and you're 10 meters deep in a freshwater lake. Using our formula, what's the pressure being exerted on you?
The answer is a pretty staggering 98,000 pascals. Think about that.
At just 10 meters down, that's only about 33 feet, the pressure from the water is almost the same as the entire atmosphere's pressure at sea level. That force builds up incredibly fast.
So let's do a quick wrap-up. The big takeaways are atmospheric pressure is just the weight of all the air above us. When you have differences in that pressure, you can create some really powerful forces, like with our can and straw. In liquids, pressure is all about depth and density. And finally, we can calculate it exactly with that simple formula, P equals rho GH.
And that really leads to one last thought. Pressure isn't just about cool science experiments. It's what drives weather systems, what makes airplanes fly. It's even at work inside your own body. So now that you know the rules of the game, where else in your day-to-day life are you going to spot this powerful, invisible force at play?